All right, guys, here goes nothing. I'm going to try this. So this is problem 32, and yeah, I'll show you the point where I like pretty much want you to go, and then the rest of it's just kind of algebra. I'll try and go through the algebra. Yeah, I won't lie. Like the algebra in this is tough, but what I want you to get is the physics of this to be able to set this up. So if you get 5 equations, you should be good with this thing. But anyway, let's get into it. So it says a solid cylindrical wheel of mass m and radius r. So we got a cylinder, basically a disc, applied to the center of the wheel at 37 degrees. So 37 degrees. There must be a 3, 4, 5 triangle in there somewhere, but I tend to just go with my trigonometric functions, sine and cosine. Anyway, all right, here we go. So force F at 37 degrees to the horizontal. See the following figure. Wow, thanks. They gave me a force diagram and everything already. I am going to go kind of faster with this guy, so I apologize for that. But then it says if the wheel is to roll without slipping, so it is rolling without slipping, what's the maximum value of the magnitude of F? And that's kind of one of the big things right here is this maximum value thing, which yeah, which I personally have missed before, and that screws up all this problem. So if it's the maximum value, meaning if I were to pull with any more force here, this thing would start to roll with slipping. So this thing would be, this disc would start to just slide, right? Because I could pull this at like a super large amount of force, but they're saying that it's still rolling with slipping. So that means you're getting this action happening here, but it's still able to. So basically, you still can say that this is static friction going on here, and yeah. And so if I'm saying that, then this is Fs max, and I can use this coefficient of static friction. So here's already going to be kind of my first equation. I'm just going to call it Fs, just for simplicity's sake, because this is going to get kind of crazy. So it's going to be mu s 0.4, which I know, times the normal force. Okay. Next up, now I'm going to do torque net equals I alpha. And so all of these forces here, the axis of rotation is right here. So the axis of rotation is about its center of mass. If it's rolling without slipping, that's the axis of rotation. So F is acting directly on the center of mass. That's not going to generate a torque. The normal force is acting opposite the direction of its r vector. The r vector for that normal force would be pointing like this. So that's not going to create a torque. The weight, not going to create a torque because it's acting on the center of mass itself. So the only thing that's going to create a torque is this friction force. Let's draw that r vector out. So it's going to be boom like this. So there's r due to the friction force. I'll call it rs so it's static friction right there. So or no, we'll just call it r, capital R, right? Because that's this right here. Okay, so that's going to be this is going to be then the torque due to the friction force. Sure, let's do it like that. Is the moment of inertia multiplied by the angular acceleration. I think I'm also going to use the fact that angular acceleration is a over r. And then this torque is going to be, this is using rf sine theta. That's any torque is equal to that. Plug that in there. And then in for the moment of inertia of a disk is 1/2 mr squared. So this is all going to end up being RF. The angle here is 90 degrees, so that's just going to be 1. Sine of 90 is 1. Is the moment of inertia is 1/2 mr squared, and then this is A over R, and then a lot of these R's are going to cancel out as a result. So that gives me the force of, or you know what, yeah, let's call it the force of static friction is going to be, so the force of static friction is MA over 2. And here's my kind of second relationship that I've just made now. So my first relationship is here. My second relationship is there. Let's see what Newton's second law tells me. So Newton's second law, if I collapse this disk into something like that, let's make it like this, make that gray. If I collapse the disk into a dot and then draw again the forces coming out of it, I would have this is F. This is the normal force. Yeah, I'm going to say Fn. And then this is mg pointing down. And then there's the static friction force pointing that way, calling Fs. This splits up into components. F cosine theta. This is F sine theta. And now applying Newton's second law, F net equals ma. And okay, so next I got here, so in the x direction, it's going to be F cosine theta minus the static friction force is equal to the mass times the acceleration. And there's one relationship right there. So that's relationship 3. And then here's the other relationship here is we got F m plus F sine theta minus mg equals 0, because there's no acceleration in the vertical direction. And that is my fourth equation. Is it 4 equations and I'm done? Well, let's see. We're going to find out. We're going to find out and see if I can juggle these 4 equations to get something that's worthwhile. So I did office hours and I played around with these equations a little bit. It does take a little bit of finesse. Like I said, this is some hairy algebra going on here. So let me see. I'm going to take Fs and plug that into there. So this is going to be, I'm going to plug equation 2 into equation 3. And so that's going to give me F cosine theta minus ma over 2 equals ma. So there's that. And that gets me to, let's see. So this is basically saying 0.5 ma. So that leaves me with F cosine theta equals 1.5 ma, I think. Yeah. All right. So there's that. That's nice. So here's relationship 5. So basically, if I can get the acceleration, I know m. If I can get the acceleration, I know theta. I know theta is 37 or something like that. If I can get the acceleration, I got this thing. So now I got to get the acceleration in some way. Let's see what I can do here. I'm going to let's see. Well, let's do Fn. Fn is going to be all the, so Fn. So this, another way to write this, so instead of saying this is relationship 4, let's isolate Fn. Fn equals mg minus F sine theta. So here's this. This is relationship 4. And what I'm going to do is I'm going to plug equation 4 into equation 1. So equation 1 is this. So FFS, or Fs, is equal to mu s, which I know, plugging that into equation 1, which is mg minus F sine theta. Yeah, let's just leave it at that. And then let's take this. So here now this is relationship 6. And I'm going to try plugging 6 into 3. So here's 3 again. So I'm going to use, yeah, plug 6 into 3. Let's see what that does. So plug 6 into 3. See where that gets me. So this is going to be, so F cosine theta minus the friction force, which is mu s mg minus F sine theta equals ma. Here we go. And now I got so ma, here's ma is all of this. So I'm going to say ma is all of this. So all of that is going to go in here. That's good. All right, so I screwed up, and so now I'm going to try this one more time. Let's see if I can do this. So this is MA here, this is MA here, and so I'm going to correct myself. So let's see if I got this. So this is going to be F cosine. Let's do something like bring it up and around. It's going to go in there, right? That's going to be MA. So this is going to be F cosine theta equals 1.5 times F cosine theta minus mu s times mg minus F sine theta. And all that. Woo! Wow. Okay. And what I'm going to do here is I'm just going to, I want to get rid of all these variables and stuff. I'm just going to do numbers. I don't want to deal with this nonsense. So this is going to be, let's zoom in a little bit here. I think I got everything in there okay. So it's going to be F cosine of 37 equals 1.5 F cosine 37 minus coefficient of friction is 0.4, I think. 0.4, yes. And then this is going to be mg. I'm just going to say g is 10, so this is 10m. Again, I'm just plugging in numbers to get rid of all this. And then f sine of 37. So there's all that. Cosine of 37 is 0.8. So this is going to be 0.8f equals 1.5, and then 0.8f minus 0.4 times 10m minus sine of 37 is 0.6f. There we go. Let's see. I'm going to divide both sides by 1.5 to isolate that. So this is going to be 0.8 divided by 1.5, 0.533. 0.8f, oops, sorry, 0.533f equals 0.8f minus 0.4. Let's go ahead and distribute that 0.4. So I'm distributing also the 0.4 here. That's going to be 0.4 times 10, I think, is just 4. So 4m minus 0.6 times 0.4. I think that's 2.4, 0.24. 0.24f. There we go. Oh, so here we go. I got like terms here. There's f and 0.2. So 0.8f minus 0.24f is going to be, so this is 0.533f equals 0.56f minus 4m. So lastly, I'm going to isolate here. So I'm going to take the 4m. I'm going to add the 4m over. And then subtract the 0.5. Let's not get crazy. So this is now 0.533 plus f plus 4m equals 0.56f. So now I'm going to subtract both sides by 0.533f. 0.5 minus 0.533f. So this is now 4m equals 0.56 minus 0.533 is 0.027. And then so lastly, divide both sides by 0.027. And I get 148, which is wrong. Hi everybody, found my error. So my error is when I did this here. 0.4, it's negative 0.4, gets distributed here and then gets distributed here. And so this negative times this negative is going to give me a positive. So this is actually positive. So now when I add up these two, it's going to be 1.04 f And now, again, I'm going to add 4m to both sides. So that gives you this. This is 1.04f. So everything is the same, except now this is going to give me 1.04 minus 0.533, 0.57, or sorry, 0.507. And then when I divide both sides, 4 divided by that gives me 7.89 or 7.9. And then this is not meters, this is mass, capital M, that they gave me for the mass. So I could write it in terms of M because they gave me that as mass M, radius R, but radius is all canceled out. Whew! Wow. I mean, that is yikes. So, yeah. Again, if you got like these 4, the rest is an algebra problem. So I'm happy if you got just those 4. But yeah, hopefully that helped, even though I made multiple mistakes as I went. All right. Take care, guys. Bye.